Why does every layer of a neural network secretly do the same thing? Grab all of space and bend it. Here is flat space with its grid. Two little arrows build all of it. I hat, one step right, and j hat, one step up. This pair is called a basis. Every other vector is just a recipe in these two. This one is two I hats plus one j hat. Think of space as a trampoline grid. A matrix grabs it and stretches it, the lines staying straight, into a brand new shape. But how do you write a bend down as just 4 numbers? Like this. So to capture a whole transformation, you only need to track those 2 arrows. Watch where I hat and j hat end up. I hat landed at 2, 0. J hat landed at 1, 1. Stack those 2 destinations as columns, and that is the matrix. The whole bend in 4 numbers. Now you can read any matrix at a glance. First column, where I hat goes. Second column, where j hat goes. Apply it, and every point rides along. Now the picture and the math, side by side. We track one point at 1, 1, and compute exactly where the matrix sends it. A rotation. The blue top row builds the new x. The green bottom row builds the new y. Watch the point move as the numbers fill in. A scaling. The blue top row builds the new x. The green bottom row builds the new y. Watch the point move as the numbers fill in. A shear. The blue top row builds the new x. The green bottom row builds the new y. Watch the point move as the numbers fill in. There is one rule a real bend always obeys. Watch the lines. A real transformation has one signature. Grid lines stay straight, they stay parallel, and they stay evenly spaced. Origin never moves. A matrix also tells you how much it stretches space. Keep an eye on this 1 unit square of area. That is the determinant, the factor the area grew by. And if it ever hits 0, space collapses onto a single line. Everything is crushed flat, and information is lost for good. That is exactly the moment a neural layer throws information away. If a matrix can bend space, can another one bend it back? Apply this transformation to the picture. Now apply its inverse, and the picture snaps back to exactly where it began. That undo matrix is the inverse. But careful, if the determinant was 0, there is no inverse. Squashed information is gone for good. In numbers, it is pure bookkeeping, and color keeps it straight. The matrix, top row in blue, bottom row in green, times the yellow vector. Blue row into the column. 2 times 1 plus 1 times 1 gives 3. Green row into the column. 0 plus 1 gives 1. Stack the 2 answers, color for color, and the point 1 lands on 3, 1. The word is surprisingly young. In 1850, James Sylvester coined the term matrix, the womb a determinant is born from. 8 years later, Arthur Cayley turned them into a full algebra, with multiplication and inverses. Today that algebra runs every neural network on Earth. And it does not stop in 2 dimensions. Add one more axis. In 3 dimensions, nothing changes but the count. A 3 by 3 matrix tracks where 3 arrows land, I hat, j hat, and k hat. Feed it a 3 by 3 matrix, and the whole cube tumbles and shears, while the camera circles so you can see it from every side. The faint cube shows where it started. Now the payoff. A single neural layer is exactly this. It multiplies your input by a weight matrix, W, that is 1 bend of space. Then it adds a tiny curve, the activation, so the bends can stack into something that is not flat. Stack enough and you can learn anything. That curve is the next season. Inside an AI, there are no pictures, only data. A cloud of points, 2 kinds tangled together. A layer multiplies every point by its weight matrix. The whole cloud rotates and stretches at once, pulling the 2 kinds apart until one straight line could split them. That is learning, as pure geometry. And it does not care what the picture is. A frog, the whole Earth, a galaxy, or a million data points inside an AI. The same 4 numbers bend them all the very same way. So drop the idea that a matrix is a static table of numbers. It is a verb. It does something to space. It rotates, it stretches, it shears. Read it as an action, and linear algebra suddenly moves. One last thing, what if you do two bends back to back, first a rotation, then a shear? Stacking transformations like that is matrix multiplication, and the order changes the answer. That is exactly where we go next. One puzzle to leave you with. When a matrix bends space, almost every arrow swings to a brand new direction. Watch the blue one turn, but this gold arrow refuses. It will not turn at all. It only stretches, staying right on its own line. That unmovable direction is called an eigenvector, the secret behind Google's PageRank and how an AI finds the few axes that truly matter. That is episode 1.8. And you can bend a real image yourself in 3 lines of NumPy. Make a matrix, multiply your points by it, and the whole picture stretches. The full notebook is in the description. In one breath, a matrix bends all of space at once. Its columns say where the basis arrows land. Rotation, scaling, shear, with the lines staying straight, and every layer of a neural network is one of these bends. A matrix is a verb. Next, what happens when you do 2 of these bends in a row? That is matrix multiplication, and it is why the order you stack neural layers matters. Thanks for watching, and keep exploring. Next time, matrix multiplication equals composition. Please like and subscribe ThirdEye Labs if you enjoyed this video, and let me know in the comments.